Hello everyone, and welcome to our first episode of Net Ionic Equations. By now, you've probably learned about balanced chemical equations, and we've used them to describe reactions of all different types. But sometimes it's better to represent a reaction as what we call a net ionic equation. And if that sounds complicated and confusing, don't worry, in a few minutes we'll have you all set up to do your own net ionic equations. Sometimes in chemical reactions, there's a lot going on, and net ionic equations help us to focus on where the action really is on the things that are actually doing the reacting. So let's see a reaction that we can write a net ionic equation for. I have some lead nitrate here. Now lead nitrate is an ionic compound, and it's made up of white crystals, and they're going to go in, and we're going to stir that around. Lead nitrate is a soluble ionic compound. Any good solubility table will tell you that nitrates are pretty much always soluble, and lead nitrate is no exception to that. So it's also important to note that when an ionic compound dissolves, the water molecules get in there and they rip apart the crystal and take the ions away so that the ions are floating around independent of each other. We call that dissociating, which is the opposite of associating. So when ions dissociate, they become separate from each other and float around the beaker independently. So you gotta imagine that. Next, I have some potassium iodide, and that is also a white solid crystal. It's an ionic compound, and iodide compounds are also typically soluble with few exceptions, and potassium is pretty much always soluble, so you'll want to have yourself a good solubility table handy in order to predict whether things are going to be soluble or insoluble. So now I have both my compounds, lead nitrate and potassium iodide, dissolved and dissociated in their respective beakers. So now I'm going to go ahead and dump them together, and we see, oh wow, look at that. Isn't that awesome? So there's this yellow stuff in here that wasn't there before. It's a yellow solid, it's clouding up the beaker. I can't see through the beaker anymore, it makes it opaque, and it's a beautiful yellow color. But what is that? And how can I represent what reaction actually just happened? Whenever you try to write equations or solve problems, it's helpful to have a series of steps that you can follow. In that ionic equation, we follow these steps. First, predict the products of the reaction and write their correct chemical formulas, making sure to balance the charges in the process, because every time you write the formula for an ionic compound, you need to balance the charges. Second, decide which product, if any, will be insoluble. Give this compound a little S for solid. Sometimes nothing will be insoluble and nothing will happen, and so you just have to determine if something's going to happen. Step 3, give all soluble compounds a little aqueous sign, because they are aqueous, they're dissolved in water, they're dissociated. Fourth, split up all the soluble compounds into separate ions, and please remember to put the charges on the ions. They are ions, they have charges, so we should write them. Also, keep the insoluble compound together, because once it forms its chemical bond, it is together and we should write it together. Then, cross out any ions that are separate and soluble on both sides of the arrow. These are our spectator ions. They didn't do anything, so we just want to get rid of them. Let's start with the complete chemical equation, which shows everything that's going on inside the beakers. I had some potassium iodide, aqueous, and lead nitrate, also aqueous. We know that because they both dissolved and became part of the solution. And then this is a double replacement reaction. The easiest way to predict the product of that is to swap the lead and the potassium, or whatever your two cations are. So let's write lead with iodine and potassium with nitrate. You might be wondering, why did I put a 2 next to the iodine and I didn't put a 2 next to the nitrate? The nitrate had a 2 on the left side, but it doesn't have a 2 on the right side. Whenever you write the formula for an ionic compound, you have to balance the charges. Don't forget to do that, otherwise you're going to end up with an incorrect formula and an incorrect balanced chemical equation, and it's just chaos. Don't assume that a subscript that appears on the left of your equation ends up on the right side of your equation. It might not, and it's best to balance the charges instead to make sure you know what the subscript should be. In this case, lead is a +2 charge and iodine is a -1 charge, so a 2 and a 1 balance with a 1 and a 2. That's why the subscript 2 went there. And potassium is +1 and nitrate is -1, so they already balance out and I don't need any subscripts. For this next part, you're going to need to predict which of those two products is the insoluble one. Precipitates happen when two ions get together and form an insoluble compound. You might need a solubility table to do this, so you may want to pause the video and go fetch one. And if you get yourself a good solubility table, you would find that potassium nitrate is always soluble. There are no exceptions to that rule. Potassium is pretty much always soluble, nitrate's always soluble, and it's soluble. Iodides are generally soluble as well, however there are a few exceptions to that rule. Like potassium iodide is soluble, but iodide with lead, silver, and mercury is not soluble, and that means our lead iodide is the insoluble precipitate. So once we've determined that the lead iodide is the insoluble precipitate, I'm going to put a little S there for solid, and potassium nitrate, which is still soluble, will get the aqueous again. The next step, which you can skip later on if you get comfortable doing these, is to write a complete ionic equation. And a complete ionic equation basically takes anything that's soluble and separates them because that's how they are in solution. So I'm going to separate the potassium from the iodine. I'm also going to separate the lead, 2+, from the 2 nitrate ions, that and that. And then I'm going to go to the other side. Now this one I'm actually going to keep together because when it becomes insoluble, they stick together, they form a chemical bond, and the water can't redissolve it, and so they are actually together. So I'm going to keep that together. But the potassium nitrate, because it's soluble and dissociated, I'm going to separate those into potassium and nitrate. It should be noted that I forgot to balance the chemical equation before by putting a 2 there and a 2 there. That's also really important. And those subscripts, those coefficients, will actually come down into your complete ionic equation. And now we've represented the things that are dissociated as dissociated ions. Please remember to put the charges on the ions that are floating around by themselves. Because they actually have a charge, they should be written with the charge. And we've kept together the thing that undissolved or became the precipitate. The last step in creating a net ionic equation is to look over your complete ionic equation and get rid of things that don't do anything. For example, the potassium ions, they started soluble, swimming around by themselves, and they ended up swimming around by themselves. So they didn't do anything, and I want to get rid of those. Those are what we call spectator ions. I like to lovingly call them loser ions, because they're at the party, but nobody wants to hang out with them. The other spectator ion in this situation is nitrate. The 2 nitrates started out by themselves and ended up by themselves and generally didn't do anything. But what really happened here was that the iodine and the lead found each other, got together, and created a compound. So they actually changed, and my net ionic equation is going to reflect those because those are not spectator ions. Those are the ones that actually participated in the reaction. And that is our net ionic equation. And you can see here that the lead iodide has now started to settle. You can see it at the bottom there. And all the spectator or loser ions are still up here in the solution. Now, for the sheer joy of it, let's do another one. I have here some aqueous silver nitrate. I've previously dissolved that. And some sodium chloride, regular old table salt dissolved in water. Watch what happens when I take the silver nitrate. The silvers and nitrates are floating around by themselves, and the sodium chlorides are floating around them by themselves, and we put them together and we get... Is that not the coolest thing you've ever seen? So now that we've got our white precipitate, we have to answer the question, what is that stuff and what is the net ionic equation? Feel free to pause the video and try to write out the complete chemical equation, the complete ionic equation, and the net ionic equation for this reaction. So if you were able to correctly predict that silver chloride is the white stuff, then congratulations, you're doing a great job. And our equations look like this. The sodium and the silver are going to swap places to make silver chloride and sodium nitrate. Sodium is always soluble, as is nitrate, so it can't be that one. And chlorides are generally soluble, except with silver, lead, and mercury. This is the exception. That's our solid precipitate. So we're going to... So then we separate anything that's soluble. These 2 get separated, those 2 get separated, and these 2 get separated. And we notice that the sodium stays by itself on both sides of the arrow, so we get rid of that. That's a loser ion. And the nitrate also stays by itself on both sides of the arrow, so we get rid of that as well. What remains is the true love that happens when chlorine and silver get together in the beaker and form the solid silver chloride.